Hello, this video is about how to show that a function is even or odd. The intensity of this video is medium. My name is Hossein Lamir Ramani. Let's recall some definitions. So a function y equals f of x is said to be even if for all x in the domain of f of x is equal to f of negative x. A function y equals g of x is said to be odd if for all x in domain of g of x is negative of g of negative x. So if we look at the definition of being even asserts that the graph of f is symmetric with respect to the y-axis. But if a function is odd, the graph of g is going to be symmetric with respect to the origin. So about the even function, it doesn't matter if you plug in x or negative x. In both cases, you get the same value. But when a function is odd and you plug in negative x instead of x, you get the negative of the value of g of x. Okay. Before going into more details about how to figure out a function is even or odd, let's start with the domain of f and g when they are even or odd. So the first thing that we check when a function is given is its domain. So the point is that if y equals f of x is even or odd, then for all x in the domain of f, we have that negative of x is also in the domain of f. In other words, if f is even or odd, the domain of f is going to be symmetric with respect to this point 0. For example, if f is even and 2 is in the domain of f, then negative 2 is also in the domain of f. In other words, if 2 is in the domain of f, but negative 2 is not in the domain of f, then f is not even. Again, if f is even and negative 1 is in the domain of f, then 1 is in the domain of f. In other words, if negative 1 is in the domain of f, but 1 is not in the domain of f is not even. The same statements hold for odd function. So if f is an odd function and 2 is in the domain of f, then negative 2 is also in the domain of f. Similar for negative 1. If negative 1 is if f is some odd function and negative 1 is in the domain of f, then we have to have that 1 is also in the domain of f. Okay, let's work on more subtle examples. Assume f of x is equal to cosine 2x plus x to the 4 minus absolute value of x. Show that f of f is an even function. So if we check the domain of f, we see that everything is in the domain of f. So domain of f is all of the real line, all of the set R. In particular, domain of f is some symmetric set. So f passes the domain test, but just passing the domain test does not guarantee that f is an even function. We have to check this definition that f of x has to be equal to the f of negative x. So let's form f of negative x. F of negative x is going to be equal to cosine 2 times negative x plus negative x to the 4 minus absolute value of x. Okay, 2 times negative x is going to be negative 2x, as you see here, plus x to the 4, because negative x to the 4 is equal to the x to the 4. And absolute value of x is equal to absolute value of negative x, so we just have absolute value of x as the last term. Therefore, f of x is going to be equal to cosine 2x, f of negative x is going to be equal to cosine 2x plus x to the 4 minus absolute value of x, which is f of x. Hence, f is an even function. So we can see 3 steps in this solution. Step 1 was the domain test. You find the domain of the function and check whether or not the domain of the function is symmetric with respect to the point 0. Then you form f of negative x. You just plug in negative x instead of x. Then you simplify and simplify until you reach either f of x or negative f of x. If you reach f of x, it means that your function f is even. If you reach negative f of x, it means that your function is odd. Let's try another example. Let g of x be x to the 3 plus sine x. Show that g is an odd function. Again, we start the solution with checking the domain. Domain of g is the set of all real numbers, r. So it's symmetric with respect to the point 0. So g passes the domain test. Now we need to check whether or not g of negative x is equal to negative g of x. Okay, we start with forming g of negative x, which is plugging in negative x instead of x. So g of negative x is negative x to the 3 plus sine negative x, which is equal to negative x to the 3 minus sine x. But this is equal to negative g of x, so g is odd. Now we do a slightly different example. Assume f of x is this piecewise function. F of x is equal to 1 if x is not 1. It's 0 if x is equal to 1. And g of x is equal to x squared. We form the function h of x, which is equal to g of x over f of x. Is this function even or odd? Okay, we start the solution by checking the domain of h. If you look at the function h, you see that in the denominator you have f of x. If the denominator is 0, for the point that the denominator is 0, those points are not in the domain of h. So we need to find for what x f of x is equal to 0. But f of x is equal to 0 if and only if x is equal to 1. So every point except for 1 is in the domain of h. So domain of h is equal to all of the real numbers except for 1. As you see here, r minus singleton 1, which means that every point except for 1. Okay, now you see that negative 1 is in the domain of h, but 1 is not in the domain of h. This means that the domain of h is not symmetric with respect to 0. So h does not pass the domain test, the domain test. And because it does not pass the domain test, we don't need to continue any further. We don't need to form h of negative h and simplify and the rest of things, because it's just the domain of h is not symmetric. It's not even, it's not odd. Okay, now I want to talk about the symmetry of the graph of even and odd function. If a function f is even, then its graph is symmetric with respect to the y-axis, as it's mentioned here. So just remember this figure. Even with the y-axis for the even function, the y-axis is significant because the even function, the graph of even functions, is symmetric with respect to the y-axis. For odd functions, the origin is a significant point because the graph of odd functions is symmetric with respect to the origin. Some examples, for instance, the absolute value of x is an even function. As you see, it's symmetric with respect to the y-axis, but y equals x is an odd function, so it's symmetric with respect to the origin. Y equals x squared is an even function, so it's symmetric with respect to the y-axis, and y equals x to the cube, it's symmetric with respect to the origin. So I want to finish this video with this question. Assume f and g are two even functions. Show that f plus g is an even function. The same for odd. Assume f and g are odd functions. Show that f plus g is an odd function. We can have this exercise for multiplication, but the scenario for multiplication is a bit different. Assume f and g are even functions. Show that f dot g, or the multiplication of fg, is even. Assume f and g are odd functions. Show that the multiplication of f and g is an even function.